Hello, everybody. Who is ready to do some chemistry? So I'm getting some great ideas from all of you on different ways that I can introduce and start off lectures. And so one idea we're going to go ahead and start with today that I really liked is to start every lecture with a couple of practice problems from things that we've covered already. And so today we're going to look at using the light equations for your practice problems. And so what I want you to do is let me bring up, here it is, there's our whiteboard. What I want you to do is to go ahead and calculate the energy of a wave with a wavelength equal to 562 nanometers. So go ahead and pause the video now and find this energy, find the energy of this wave, and then restart the video and we'll go over the answer. Okay, really, pause the video. I mean it. Don't just wait for the answer. Pause the video and do this problem. Okay, and now you're back. So let's look at how we would go about this. And so we've got two basic equations that we use when we're looking at any of these light equations and this light work. To calculate our energy, that's going to be Planck's constant times the frequency. To find the frequency, we're going to use the relationship between the speed of light, wavelength, and frequency. A couple ways to do this. You could either rewrite this equation. So frequency is going to equal c over lambda. You could then take this and put it right in here for lambda, end up with E equals hc divided by lambda. You could go about it that way, then just plug in your numbers here and find the energy. I usually honestly like to do these in two steps. I will usually use my rewritten equation here first to find my frequency and then plug that into the energy equation. It's just the way that I learned how to do it when I was sitting where you are. And so it's the way that I still do these problems today. And so I'm going to take the frequency equals C, remember 3.00 times 10 to the 8th meters per second over the wavelength. Now, the big thing to remember here, and one of the most common mistakes that I see in this type of problem, is that in this light equation, your wavelength has to be in meters. However, quite often we are given wavelength in nanometers or in different units. So we must convert this first before we put this into our light equation. And so when we convert 562 nanometers over to meters, we get 5.62 times 10 to the negative 7th meters. Now we're ready to go ahead and use our equation. And so we do out the math of this and we get 5.33 times 10 to the 14th hertz. Now note here as well that quite often when we're working with energy and with waves in this sort of range, this is the sort of frequency that we're going to get quite often. You're very often going to get things in the range of times 10 to the 14th, 15th, 13th, somewhere around there, but some fairly large numbers. We can now take this and plug it into our energy equation. H, remember it's Planck's constant, 6.626 times 10 to the negative 34th. The units are joules seconds. We multiply that now by the frequency we just found, 5.33 times 10 to the 14th hertz. We do the math of this and we get 3.54 times 10 to the negative 19th joules. And that is our final answer. Now again, also note that when we're finding these energies, what we're actually finding is the energy of a single photon. That's the part that's quite often missing, is that information. That we're finding the energy of one single photon. So we're going to have very small numbers for these. Times 10 to the negative 19th is very, very typical for this type of problem. And so keep that in mind when you're working these sorts of lights equation problems, where we're finding the energy of one single photon. That's going to be a very low number. You might also run into problems where instead of just one photon, you might be asked to find the energy of a mole of photons. Okay, then we're just going to multiply this by Avogadro's number. And so there is an example of the light equations. And so I hope that was helpful. Great idea from the person who suggested that, and I think we will stick with that for most of our lectures. I will try to do some example questions. And so today, what we're going to get into now is looking in a lot of detail at how elements actually bond together into compounds. And from there, we're going to move into, that'll give us the ability to move into our next lecture to actually looking then at how compounds are going to be shaped. And because there's a definite three-dimensional shape to compounds, which gives rise to a lot of the different properties. The reason that water has all the properties that it does, and water, if we haven't really talked about it yet, is very unique in some of the properties that it has a very high boiling point compared to other compounds of a similar size. And a lot of that comes down to the shape that water has. And again, we're going to be talking about a lot of this in our next lecture, and then some of the properties after that. But the shape of water really is bent like this, with oxygen here in the middle, and then the two hydrogens coming off down at an angle. These little bulbs here will be some electron clouds that are hanging above oxygen. Again, we're going to get into all of that. But water would not have the properties that it does. Water would not have the high boiling point that it does. Water would not have the surface tension that it does, and the ability to bead up like it does, if it didn't have this bent shape. And so the shape of molecules is key to looking at how the molecules are going to behave, to looking at some of the properties of those molecules. There's an expression, especially in biochemistry, where we're starting to look at bigger and bigger and bigger molecules, that form equals function. That basically the shape of large biomolecules gives rise to almost all of its properties. And so we have to start at the very beginning by looking at the shape of individual smaller molecules. And so that's what we're going to be building to, is eventually being able to look at that. And so some things that we have to think about, such as what actually holds the atoms together in a covalent molecule or an ionic compound. Why are some of the atoms often at different angles? Why does water have that bent shape like it does? Why are molecules three-dimensional to begin with? And then finally, can we actually predict the structure of a compound? And then finally, looking at how that structure relates to chemical and physical properties. And so we've talked a lot in this unit so far about electrons. It's been all about electrons, looking at how electrons are arranged around the nucleus, and seeing that there's a definite order to how electrons are arranged. And so, for instance, with an atom like carbon, maybe, for instance, and so we look at carbon, atomic number equals 6. Therefore, in a neutral carbon atom, we have 6 electrons that we're going to be worried about. We've got our nucleus there in the middle, and we know those 6 electrons exist on these Bohr shells that we've talked about. 2 of those are going to be on the first Bohr shell. The other 4 electrons are going to be distributed along the outside. Now, it turns out that it's actually these outermost electrons here. It's these electrons here on the outer shell that are actually going to be driving how carbon behaves. And so we're going to differentiate between our outer electrons and our inner electrons. The other term that we use, or the official term, are our core and our valence electrons. The valence electrons are the electrons on the outermost Bohr shell. When we're looking at that, we ignore sublevels. We're looking at just the very outer Bohr shell. And so when we're looking at the example of carbon, at these 4 electrons here, we're not paying any attention to the fact that, so if we look at the configuration, the electron configuration, 1s2, 2s2, 2p2, when we're determining core and valence electrons, it doesn't matter that these 4 are in an s sublevel and a p sublevel. That doesn't matter. We just look and see that there are 2 electrons total out in the second Bohr shell, out in that outermost Bohr shell. And so that means that carbon has 2 core electrons and 4 valence electrons. Sometimes it's easier just to count up the valence electrons And then we know that anything that is left over is a core electron. So again, we know that there are 6 electrons total in a neutral carbon atom. We can look at our configuration or a little diagram like this and see that 4 of those electrons are in our outer shell. The rest of them have to be valence electrons, those last 2. And so we see a couple other instances of that here, a couple other examples. Here we have oxygen with its 8 electrons. Again, 2 of those here on our first Bohr shell. The other 6 are all distributed on the outer shell. So there are 6 valence electrons in oxygen. Neon, 10 electrons total, 2 of those on our outer shell, and then 2 of those on our inner shell, and then 8 along here on our outer shell. So neon would have 8 valence electrons total. And again, we can look at the electron configurations to determine that. We can see that in the case of oxygen, we have electrons in 2s and in 2p. Those are all in the outer shell. And so there are 6 electrons total in the outer shell of oxygen. And so there are 6 electrons in the valence shell. There are 6 valence electrons. And there are 2 core electrons. And we have the diagram of that here. And we'll talk about some of this pairing up versus non-pairing up in a little bit. That's definitely part of what we talk about and we'll look at. But we can see, actually, we can talk about that right now. Let's just take a look at where that comes from. So remember box diagrams. So we have our electron configuration here for oxygen. So we've got 1s2, 2s2, 2p4. If we do our box diagram or our arrow diagram for oxygen, so here's 1s, 2s, and those 3 are our 2p. So here's 1s2, and then 2s2, and then 2p4. Remember Hund's rule tells us we're going to fill the 3 individually. Then we're going to come back around and fill in the other, and fill in the first p orbital. So that's where this comes from. So we're looking, remember, at these 6 electrons here. These are our valence electrons. We can think of these as maybe being the 2 that are paired up into s. These are the 2 that are paired up in the first p orbital. And then those are our singlets. And so that's just, we're able to depict that pairing up in orbitals when we're looking at a diagram like this one. And so hopefully you're at the point now where you're asking yourself, okay, well, is there an easy way to find out how many valence electrons there are in an atom? Because as I mentioned, it turns out that it's the valence electrons and the number of valence electrons that really drive how an atom is going to behave. It drives the properties of that atom, how that atom is going to interact with other atoms, how it's going to bond. And so hopefully there's a really easy way to see how many valence electrons there are in an atom. And so ask yourselves, can I count to 8? Hopefully you all said yes. If you can count to 8, you can find the number of valence electrons. We use our old friend, the periodic table. This is another one of the ways that the periodic table is arranged. If we skip the transition metals, remember we have that weird dynamic with the transition metals with the 3D being filled after 4s and so on. So if we're thinking about the main group elements, everything in the first group, the first family, the alkali metals, 1 valence electron. Alkaline earth metals, 2 valence electrons. 1, 2, then we skip. Everything in the aluminum family, so to speak, 3 valence electrons. Carbon family, 4, 5, 6, 7, 8, with the exception of helium. Helium is a bit of a weirdo, but we'll talk about why helium is a little bit different in a little bit. But everything else has 8 valence electrons in the noble gases. And so literally just count over in the periodic table and skipping our transition metals. But if you count how many spaces over an element is, That's the number of valence electrons. It's that easy. We just count over how many spaces from the left an atom is in the periodic table. We have another way that we can depict this, and we're going to use this quite a bit. We'll use this more later, but I want to introduce it right now. We have what we call Lewis dot structures or Lewis dot symbols, where we symbolize all of our valence electrons as dots written around the atom. And so in the case of a couple of our alkali metals, lithium and sodium, one dot signifying one valence electron. Our alkaline earth metals, beryllium, magnesium, and so forth, two dots signifying two valence electrons, and so forth. Three dots for boron and aluminum, four for carbon and silicon. Mouse is messing with me today. Five for nitrogen and phosphorus, and so forth. Now, it doesn't matter where you actually place them. This dot for lithium could have been placed over here, could have been placed down here. That doesn't really matter. But when you're drawing the Lewis structures for individual atoms, you don't want to double up until you have to. Same idea as Hund's rule, sort of, where we're just going to put atoms singly until we start to have to double them up. And then we'll eventually get to 8 around our atom for our noble gases. And so just do a bit of a check. And so how many valence electrons are in phosphorus? Check the periodic table, look where phosphorus is located. Hopefully you found 5. How many valence electrons in chlorine? Again, just use the periodic table while I scratch my ankle. That's much better. Chlorine has 7 valence electrons. And finally, carbon. Check that one while I get a drink of water now. Carbon has 4. Okay, so what? How are we going to use that? Why does this really matter? We're going to use this in a number of ways. The first way that we're going to use this information of these valence electrons is really taking a closer look at bonding and how atoms are going to be held together in compounds and molecules. And so we've talked about some of these a little bit, but we're going to start getting into more detail now. In a covalent bond, when we have especially like two nonmetals coming together, covalent bonds result from electrons being shared between the two atoms. Now, again, we're looking at electrons in the outermost shell. It's just those valence electrons which are now going to be shared to form a covalent bond. In an ionic bond, we have a full electron transfer, again, coming from the outermost shell into an innermost shell is one way we can view it. So in the case of maybe the ionic bond between sodium and chlorine, we have one valence electron from sodium, leaves sodium completely, and enters into the valence shell of chlorine to form the chloride ion. Now we have a positive and a negative, and they're going to come together and hold together from that electrostatic interaction. We also have metallic bonding, which we're not really going to get into much in this course here. But with metallic bonding, for instance, if we're looking at a pure gold bar, fortunate enough to maybe have a nice big gold bar, the bonding between the gold atoms in there, really what sort of happens there is that the nuclei of the atoms are lined up, are sort of stacked up in there. And then rather than a sharing between atoms or a transferring between atoms, all of the valence electrons are sort of mobile throughout the whole entire structure, whole entire complex. They're not necessarily localized or shared between two of the atoms. They're just sort of free floating. That's one of the properties that gives metal its conductive properties. One of the reasons that metals conduct electricity so well is because of that free flowing of electrons in metallic bonding. Now note here, and we're going to see this again in a little bit, we talk about bonds as if a bond is covalent or as if a bond is ionic. The reality is that this is really much more of a continuum. where something we might say is purely covalent if there's a complete equal sharing. As that sharing starts to become a little bit more unequal, as maybe one atom hogs the electrons a little bit more, we start to get what we call polar covalent, and that compound starts to look a little bit maybe more and more ionic until we finally get a complete charge separation. And really, like I said, there's a continuum there between covalent and ionic. We do talk about it more as if it's concrete. This is covalent and this is ionic, because that makes it a little bit easier for our discussions. But it is much more of a continuum that exists. So just keep that in mind. So here we see, like we've seen before when we talked about ionic structures, here we have a sodium and a chlorine. We see the Lewis structures for each. There's our 1 valence electron for sodium, our 7 valence electrons for chlorine. And so this valence electron from sodium is going to leave and enter into the valence shell for chlorine. So since sodium is losing 1 electron, that makes it a positive ion. Chlorine gains 1 electron to make it a chloride ion. We now have, we will now have an ionic compound because the pluses and minuses will be attracted. Most of our discussion in the next week or so is going to center more around covalent compounds. So we have a shared pair of electrons, or more than one pair in some cases, as we'll see, shared amongst our valence electrons. And typically we're talking here about nonmetals to nonmetals. Quite often when you see a metal present, that's a signal that the compound is likely ionic. And we talked about that when we looked at how to name compounds. A metal with a nonmetal would be ionic and subject to those rules. A nonmetal with a nonmetal would be a covalent molecule and subject to those naming rules. So we've talked about some of this already. We're just going into some more detail on what actually happens. Now, in order to look at really what it's going to be, is it going to be ionic or is it going to be covalent? So far, and again, in our discussion of naming, we sort of left it at metal and nonmetal ionic, nonmetal and nonmetal covalent. We're going to go deeper into that and really look at the reasons for that now, looking at something we call electronegativity. Electronegativity is the tendency of an atom to attract the electrons in a chemical bond. And so atoms with a higher electronegativity, when they are in a bond, the electrons that make up that bond will spend more time near that atom with a higher electronegativity. And so, in other words, let's look at a couple examples here. If we have, for instance, maybe just, let's look at one of our diatomic molecules. Let's look at just something simple like Cl2. So just a chlorine diatomic molecule, Cl2. It's going to form a bond, so Cl to Cl. And these 2 electrons here, so we have 2 electrons that make up this bond between the 2 chlorine atoms. The electronegativities are the same because it is the same atom, obviously, and so we don't have a large electronegativity difference. And so those chlorines essentially are going to share those 2 electrons equally. Remember, electrons are sort of in constant motion, always moving around all the time. And this means, though, that since there's no difference in our electronegativities, that the electrons aren't going to spend more time closer to one chlorine than the other. They're going to be around each chlorines equally. Let's say now, though, that we have, and again, we're going to look at some of these structures in a little bit, so don't worry too much about the structure that I draw. But let's say we have this compound here, CH3F. And let's pay particular attention to this CF bond right here. In the CF bond, now we do have a difference in electronegativity. It turns out that fluorine is actually our most electronegative atom. And so we have a fairly large difference. And we're going to look at what the values for these differences mean in a second. We have a fairly large electronegativity difference of 1.5. It's hard to math. So a fairly large electronegativity difference here. That means that when we look at this bond in a little bit more detail, let's just blow this up a little bit. Here's our 2 electrons that make up the bond. So those 2 electrons, again, are always moving around. And for our purposes in this discussion, we're going to say that those 2 electrons are always going to be between carbon and fluorine. They're always making up that bond. They're what are holding carbon and fluorine together. But since fluorine is so much more electronegative, the electrons want to be around fluorine more. And so they're going to spend more time closer to the fluorine. On average, they will be closer to the fluorine than they will to carbon. They're still in between carbon and fluorine. They're still making up that bond, but they're going to spend more of their time near fluorine. That's what electronegativity is all about. And so remember that continuum that I mentioned earlier between covalent and ionic? It really comes from electronegativity differences. And so when we have an electronegativity difference that's between 0 and 0.4, we call that a pure covalent bond. There's not enough of an electronegativity difference there. For instance, with our carbon-hydrogen bonds here, so with these 3 bonds, carbon has an electronegativity of 2.5, hydrogen has an electronegativity of 2.1, right on the border, a difference of 0.4, but that means that there's not enough of a difference for us to really to worry about, so to speak. The electrons in these bonds here are going to be shared equally between the carbon and the hydrogens. Now again, these electrons are always going to be between the carbon and this hydrogen. These electrons will be between this hydrogen and this carbon, and so on. But that's an equal sharing because there's not enough of an electronegativity difference to make the bond polar, which is something that we'll talk a fair bit about later on. And we'll introduce the word here. In a polar covalent bond, now we run into the situation like we had with carbon and fluorine. So if we have an electronegativity difference between 2 and 0.4, now we have enough of an unequal sharing that the electrons spend more of their time near one atom than the other. That creates what we call a partial negative or a partial positive charge. It hasn't created what we'd call a full charge like on an ion, but the electrons are spending enough of their time near one atom that one atom sort of starts to look negative. And the other atom sort of, a little bit, starts to look positive. That's what we mean by this partial negative and partial positive. Finally, we get to enough of a difference that we can say that one of the atoms, like between lithium and fluorine, for instance, and so lithium with an electronegativity of 1, fluorine with an electronegativity of 4, difference in electronegativities of 3, now we say that's enough of a difference that the fluorine loves the electron so much in comparison to lithium that it's just going to take it. There's no longer going to be this sharing. Fluorine's just going to grab it. And that electron is going to go with fluorine and create a full-on negative charge, as opposed to the lithium, which then lost that electron, created a full-on positive charge. And so, like I said earlier, there's this continuum. And so if we have absolutely no difference, if there's an electronegativity difference of 0, so something like Cl2, 100% absolutely purely covalent, electrons 100% shared equally. We start to get a little bit more of an electronegativity difference and a little bit more. Finally, we get enough of an electronegativity difference that we say one of these atoms is starting to look a little bit negative. Just a little bit, but starting to have some negative character. Until we build that up even more. Get enough of a difference there, and then finally we get to a difference of 2, and we say, all right, this atom no longer just has a little bit of negative character. This atom's full-on negative. This atom stole the electron. This atom has a full-on negative charge now, and then all the way up to a giant difference. And so that's really the ionic versus covalent. That's the continuum that I talked about. Again, for our purposes, we do talk about it more in definitive terms. So we're going to say that any electronegativity difference greater than 2 is an ionic bond. Any electronegativity difference lesser than 2 is a covalent bond. anything between 0.4 and 2, or 0.4 and above and 2 is a polar covalent bond. And we'll be using that term polar and that quite a bit, especially when we get into shapes and properties in the next lecture. And so a chemical bond, like I said, it's that force that holds two atoms together. The bonding occurs between valence electrons. We've talked about how electrons in an atom will be categorized as either valence or core. Atoms will try to get 8 electrons in the valence shell, as long as it's big enough, and we'll look at some exceptions there. But essentially what atoms are quote, trying to do when they form bonds is to attain the same type of electron configuration that a noble gas has. Noble gases have 8 electrons in their valence shell. That's what every atom ideally would like to do. Whether it does that through a stealing and a transfer of electrons in an ionic bond, or if it does so through the sharing of electrons in a covalent bond, atoms ultimately are trying to get 8 electrons in their valence shell. And that's going to dictate much of what we do over the next week or so. And so we're going to use Lewis symbols to help us track the valence electrons and predict the bonding in compounds. And so the Lewis symbols that we introduced earlier, I'm just getting a little bit of a lozenge since I've been talking so much. The Lewis symbols that we introduced earlier for elements, we're now going to expand those to entire compounds. And so we're going to use our valence electrons, so our electrons from the highest n. We're going to follow what we call the octet rule, where we're going to try to get 8 electrons in every atom within the compound. And again, this really is only useful for what we call the main group elements, everything except the transition metals. So we're looking at our alkali and alkaline earth metals, our S block and our P block, essentially. We're ignoring all of the transition metals when we look at Lewis symbols and Lewis structures. But for anything that is in our main group, our S block and our P block, we can create Lewis structures for various compounds. And so let's look at how we do this. Sorry. And so again, what we're trying to do here is keep track of the electrons around atoms, ions, and molecules. And we're going to use our Lewis or our valence electrons to do this. And so again, for one element, and we sort of looked at this already, if we're just doing one element, we're going to draw the atomic symbol. We're just going to have a generic element here, X. That's going to be representative of our nucleus and all of the core. Ooh, again, finding so many typos with your class. Electrons, fixed. So that X is our nucleus, and all of our core electrons are all represented there. Then we're going to treat each side like it's a box that can hold up to 2 electrons. And so we're going to count the electrons in our valence shell, and then we're going to start filling the boxes. And we're not going to pair anything up until we actually have to. And so, like I mentioned, it doesn't matter what side you actually put what side you start on. It's all the same thing. It's all equivalent. So we saw this slide already, just looking at the Lewis structures of various atoms. And so try a few on your own. Let's look at the Lewis structure for carbon. So first we're going to start with the Lewis structure. We're going to start with our configuration to find how many valence electrons, or you can just use the periodic table and count 1, 2, 3, 4. Now see if you can draw the Lewis structure. Hopefully you came up with this. There's our Lewis structure for a carbon atom. Now, as we start to look at the Lewis structures Lewis structures of compounds, now we're going to start looking at how a whole compound is arranged. 2 dots signify a chemical bond. And so you can either write a bond as two dots. These are two electrons forming one bond, or one line. This one line signifies two electrons. So like in this example here, here's Cl2, a chlorine-chlorine bond. We can either write that as two electrons making up the bond, or this one line signifies two electrons. So either way, personally, I'd recommend using the lines. It just makes things a little bit more clear and a little easier to see. Just always remember that that line represents two electrons. We're also going to look at what we call lone pairs and bonding pairs. So let's actually look more closely at that Cl-Cl bond. So if we draw out so there's our Lewis dot structure for one chlorine. Go ahead and draw on the other chlorine. So there's the other chlorine atom. Now again, when these two come together, we're going to have in our bond so that's just, I just drew it in different colors so we could see where the two different atoms and where they're coming from. And so again, let's just sort of step back and consider our octet rule. And so in each of these, chlorine has 7 valence electrons. The octet rule tells us that chlorine wants to have 8 valence electrons. And so it's going to do that by sharing this electron here in each one. And so that's what we have symbolized here in our bond. So now each chlorine has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, because we say that these 2 electrons here are now shared between the atoms. So each atom has an octet. And so now let's differentiate between, just write this out with a line. Let's keep all of the valence electrons in there, because these other valence electrons, as we'll see later, still play a role in determining properties. And so what we have are the 2 electrons that make up the bond. We call those a bonding pair. They're making up the chemical bond. We also have around each, we have 6 lone pair around each chlorine. And so this is terminology that we're going to use as we are making our Lewis structures. Lone pair versus bonding pair. So take note of what that really means. We're going to use our octet rule. One thing to remember is that for when we're making octets, the octet rule really means 2 for hydrogen. We can only ever fit, hydrogen's tiny. Hydrogen will only ever fit 2 electrons around it. So when we say octet, what we really mean is a full outer shell. For most atoms, that's 8 electrons in the outer shell, but hydrogen's so tiny that it means 2. And so keep that in mind as well. And so when we look at some examples of some Lewis structures, and so H2, and we'll see how to come up with these in just a minute, but our Lewis structure for H2 is just going to look like this. We have 2 valence electrons, and they're going to be held together. The hydrogens are going to be held together with those 2 valence electrons. HF. Now we have some lone pair around the fluorine. And we're going to talk about how to come up with these. Don't worry about that. We're just showing some examples now. So like I mentioned earlier, the electron pair can be either the bonding pair, either represented by a pair of dots or as a line. And we call these Lewis dot structures in honor of scientist named G.N. Lewis. Oh, that's right. And I have some depictions of these. So here we go. Here's our H atom, the H2 molecule. Let's do that slower. So there's one H atom. Now here's the second H atom coming in. Now they're sharing their electrons, and there's HH, H2. So we'll look at F2, or sorry, HF. So H and F coming together. And again, we've looked at these already. This is just another depiction of it. But here we have a bonding pair. And then we have 3 lone pairs around our fluorine atom. And we call this a single bond made up of just 1 pair of electrons. We'll see some other examples later where we have multiple pairs of electrons forming what we call multiple bonds. Another thing to think about when we're making our Lewis structures is what we call the covalency, which is the number of bonds that an atom typically wants to form. And so we look at how many electrons from other atoms are needed to form an octet. Now, there can be exceptions to these, and we're going to see some exceptions to these, but looking at the covalency is a good place to start when you're looking at making Lewis structures of compounds. So for instance, hydrogen has 1 valence electron. That means it has a covalency of 1 because it only wants 1 more electron in order to fill its valence shell. Chlorine has 7 valence electrons, so it also has a covalency of 1 because it only wants 1 electron to fill its valence shell. Oxygen, 6 valence electrons. There's a covalency of 2 electrons to fill its valence shell, and so forth. And what the covalency tells you is how many bonds that an atom will typically make. Again, there are exceptions, and you'll see some exceptions, but looking at the covalency is a good place to start when you're looking at how to initially set up some Lewis structures. And we're going to look at tons of examples of Lewis structures in a couple minutes. So here's H2 and Cl2. Let's get into how we actually write them, though. So let's look at our rules for drawing a Lewis structure. So the first thing that we're going to do is count our total number of valence electrons. Let's look at the examples that we've already done. Let's look at HF. And so our total number of valence electrons, we use our periodic table. Hydrogen has 1 valence electron, fluorine has 7. So we know we have 8 electrons total that we need to deal with. So there's our first step. Anytime you have an anion, if you're doing some polyatomic ions, you add 1 electron for each negative charge. Cations, we'd subtract 1. So just as an example, if you're doing the configuration of, or the Lewis-Stock structure of carbonate, CO3 2-, we're going to see that we have 4 electrons on carbon, 4 valence electrons on carbon. We have 6 valence electrons on oxygen, and we have 3 of those. So we have 18 total coming from from oxygen. We add our 4 and our 18 to get 22 electrons, but our 2- tells us that we add another 2 electrons. So if we were doing the Lewis structure of carbonate, we're actually going to be working with 24 electrons total. So I just show that so that you see how you adjust your number if you are doing this for ions as well. But let's just go ahead and erase this for now so we don't confuse ourselves. And we'll continue on with our rules for looking at HF. The next thing we do is write out our skeleton structure. Generally speaking, the least electronegative atom will go in the center. Hydrogen and fluorine will always be in what we call terminal positions on the ends. But with HF, that's easy enough. I mean, I've already written it out here. But we're going to write out our skeleton structure with H and F. And then we're going to place 1 pair of electrons between our bonded atoms. So there's 1 pair of electrons right here. We're just going to connect everything with single bonds. Again, this is simple, just HF. We'll look at some more difficult examples here coming up. But here we have HF. And so now we've used 2 of our electrons. So we still have 6 electrons that we need to place around our Lewis structure. We do that by adding electron pairs, and we start with the outer atoms. So we're going to start adding lone pairs of electrons to fill the outer atoms. So we've added 6. I'm ignoring my number here to start out. We've added 6 around fluorine because that's what completed its octet. So then we subtract our 6, and now we see that we have no more electrons left. We've used all of our electrons. And so we have a complete Lewis structure now for HF. And then any remaining we would place on the central atom. Let's say we didn't use all of our electrons here, and we had something that wasn't just linear like this. Any electrons that are left, we're going to place on our central atom as lone pairs. And we'll talk about this and now our last thing would be to check to see if every atom has an octet. If not, we're going to move electrons around to form multiple bonds to get every atom to an octet. 2 overriding rules in Lewis structures. So I mean, you go through these steps, and we're going to see several examples. But the 2 overriding rules: use all of your electrons, use the exact number of electrons that you have to work with, and every atom gets an octet. If you're satisfying those 2 main rules, you will have a correct Lewis structure. We'll talk about how you might be able to come up with even more than one correct Lewis structure for a compound. And we're going to talk about how we would determine which one is correct or which one is more likely to exist. But if you're satisfying those 2 rules, then you have a correct possible Lewis structure. Use all of your electrons, every atom gets an octet. Overarching rules in Lewis structures. Some caveats and some hints and things that you'll see, but those are the 2 biggies. Hydrogen atoms will never, ever, ever have lone pairs or multiple bonds. Ever, ever, ever. Hydrogen is just too tiny. It will only ever exist in a terminal position with 1 bond, and that's it. Let's apply these rules to carbon tetrachloride. Very carcinogenic compound, not a good compound you would ever want to play with. But let's look at applying our Lewis structure rules. So carbon, 4 electrons. Chlorine, we have 4 of them. We look on our periodic table and we see that there are 7 valence electrons in chlorine for a total of 28 electrons from chlorine, which tells us that we have 32 electrons total that we have to worry about in this compound. And so then we're going to write out our skeleton structure. We're not going to connect anything yet. We're just going to place the atoms. The least electronegative atom in the center. So we look on our periodic table, and one thing, sorry, that I didn't point out, let me go way back to that because this was very key. And I just realized that I completely forgot it. Let's go back to our electronegativity slide. So one thing you can do is just look at the numbers, absolutely, and you'll never have to memorize these. If you need the electronegativity values, you'll have them in some way. But we also have this trend. Electronegativity increases as we go up and to the right. And so we can even look at just carbon and chlorine, and we can see that chlorine is so much further to the right that chlorine is going to be more electronegative. And again, if you need to, look at values. Take a, print this slide out maybe, have these values available, and look and see that chlorine is definitely more electronegative. And so we see that carbon is the least electronegative atom. There we go. So carbon's going to go in the middle. We're then going to place our other atoms around carbon, leaving carbon central. So there's our skeleton structure. There's step 2. Step 3, we're going to place 1 pair of electrons between the bonded atoms. In other words, we're going to connect every atom to the central atom using 1 single bond. Now let's keep track of our electrons. We've used now 2, 4, 6, 8 of our 32. So we've used 8 electrons. So we have 24 more electrons that we need to place. So now we're going to take those, we're going to start taking some of those 24 and placing them around the outer atoms first in order to form octets. And so each chlorine needs 6 more to form an octet. And so now I've placed those electrons to form octets around each of my outer atoms. And I can see that in each case, I used 2, 4, 6 times 4 total, means that I have now used up another 24 electrons. I have no electrons left. So there's one of my overarching rules for Lewis structures. I've used all of my electrons. Now let's check to see if everything has an octet. Carbon has 2, 4, 6, 8 electrons around it. Carbon's good. Chlorine, 2, 4, 6, 8 electrons around it, and every chlorine is the exact same. Every atom has an octet. I have a correct Lewis structure for carbon tetrachloride. Easy as that. Let's look at a few more examples. So here we have PCl3, phosphorus trichloride. So again, we're going to count up our valence electrons, 5 from phosphorus, total of 21 from chlorine, 3 times 7. So 26 electrons total for PCl3. We're going to start with our least electronegative atom in the center, and connect everything else by single bonds. We've now used 2, 4, 6 of our electrons, so we have 20 more electrons to place. And so we're going to start by filling the octets of our outer atoms. So each chlorine is going to get 2, 4, 6. Now each chlorine has an octet, but now I've only used up 18 of that 20 that remained. I still have 2 more electrons. Now I'm going to go ahead and put those then on my central atom. Now, and that fills the octet for that atom. And we look and we see that in fact, we've used all of our electrons. Every atom has an octet. Here's a correct Lewis structure for PCl3. Now you might find that you might run into a situation where you run out of electrons. So we've used all of our electrons here. Let's actually go through this one. Here we have HCN. And so HCN, 1 electron from hydrogen, 4 from carbon, 5 from nitrogen. So we have 10 electrons total. And so we start with carbon in the middle, our least electronegative, hydrogen and nitrogen. We do single bonds, and then lone pairs around our outer atoms, and then boom. So now we've used up all of our electrons. So I just walked you through the process pretty quickly for how we get to here. So we've used all of our electrons, but carbon does not have an octet. Hydrogen does. Remember, hydrogen's octet is 2. Nitrogen's got an octet, 2, 4, 6, 8, but carbon's only got 4 around it. So what we're going to do is we're going to steal some of these lone pairs from around nitrogen and put them into bonds around carbon. But we're going to, instead of having this lone pair here, we're going to dump it into a bond and see what that does. And what we'll see, in fact, so let's actually come back to the slide and do this out. So what we're going to do first is we're going to take one of these lone pairs and we're going to dump it in right here. So we're just going to move that lone pair to form what we call a double bond. Good enough. And so all we've done is moved it. We haven't changed the number of electrons. We've just moved the location from a lone pair to now it's in a bond. And so we've moved the location of these 2 electrons to form a double bond now between carbon and nitrogen. And so let's check. Carbon now still only has 6 around it. Hydrogen still has 8, 2, 4, 6, 8. So hydrogen's still got an octet. But carbon's only got 6. So what we're going to do then is go ahead and move another one. Let's dump another lone pair in there. We haven't done anything between carbon and hydrogen. Now each atom has an octet. And so if you use all of your electrons, but the central atom still does not have an octet, move some of those lone pairs into bonds instead and start forming double or even triple bonds, such as the triple bond here between carbon and nitrogen. So another check. So here we have carbon dioxide, CO2. I'm going to put our C in the middle, least electronegative. We have 16 valence electrons total to work with. We're going to start here, single bonds between our carbon and oxygens. And then we're going to place our lone pairs along our outer atoms. And we see that we've used 16, so we've now used all of our electrons, but carbon doesn't have an octet. So we're just going to steal some of those electrons. We're going to steal a lone pair from this oxygen, dump it into the middle. We'll steal a lone pair from this oxygen and dump it in the middle. And we end up with 2 double bonds between our carbons and our oxygens. Now, just as a preview, I don't even know if I want to go here, but I will. Why not? So when we started from here, from this point, and what we did is we just stole a set of electrons from each oxygen and dumped it into a double bond. There's actually no reason that we couldn't have done this and ended up with a triple bond and a single bond. Now here, every atom has an octet. We've used all of our electrons. This would be a correctly drawn Lewis structure. It meets all of our rules. But a couple things that we want to consider. Remember that covalency that we talked about? Carbon wants to form 4. And for our purposes in this course, carbon's never going to form anything other than 4 bonds. So it's going to have 4 bonds. Oxygen's covalency is 2. Ideally, oxygen would like to have 2 bonds. Now, there will be cases that we'll see where it doesn't. But in an ideal situation, oxygen will have 2. So if you can draw a Lewis structure that has oxygen having 2 bonds, that's going to be the preferred one. And so it is definitely more correct to draw this Lewis structure compared to the one with a triple bond. We're going to evaluate what we call formal charges in a few minutes to see really why this is. But for now, one of the things to look at is that covalency that we talked about earlier. Oxygen wants to form 2. So keep that in mind when you're making your Lewis structures as well. So here's another example, formaldehyde, CH₂O. So we count up our valence electrons, 12 total. Carbon's the least electronegative. We'll put that into the middle. We'll put our other atoms around on the outside, remembering that hydrogen will only ever form 1 bond. We're going to connect them with single bonds. We have 6 electrons left, so we're going to start to place those as lone pairs around our outer atoms, never lone pairs on hydrogen. So we're going to place all of those 6 on oxygen. But now we see that now we've used all of our electrons, 2, 4, 6, 8, 10, 12. But we see that carbon does not have an octet. And so we'll go ahead and move one of these lone pairs into a double bond between carbon and oxygen. So there we have a correct Lewis structure for formaldehyde. Now again, there are a couple different ways that you could write this. You could write this with oxygen as our central atom. You could write this linearly, like this. Both of these structures meet our guidelines for Lewis structures. They hit our 2 primary rules. But again, we can see that both of these have issues with the covalency. We have atoms without their preferred number of bonds. So that's one thing that starts to tell us something's a little bit squirrely here. And then again, we're also going to look at something called formal charges later. Another thing to look at is that nature likes symmetry quite a bit. And we can see, I mean, yes, this one is symmetrical, but our least electronegative atom is not central. But this isn't really symmetrical in the same way that this structure is. That's another thing to just sort of keep into the back of your heads. Sorry, but again, we'll also look at what we call formal charges in a few minutes to really see why this one is the favored structure. And so take a few minutes now, go ahead and pause the video, and draw these Lewis structures out. I don't have the answers to these, or actually I will. I'll pause the video too, and I will come up with the answers to these that I will put up on the whiteboard. So go ahead and pause the video and draw out these Lewis structures and see what you come up with. And we're back. Hopefully what you have come up with, oops, didn't mean to start up FaceTime. But hopefully what you have come up with is, or are, these three structures here. Now you might be asking yourselves, is it really important? Do I really have to worry about the lone pairs on each, especially in cases like this? And the answer is absolutely. If you do not draw these lone pairs around the outer atoms, that is incorrect. You have to have those lone pairs drawn. And so for the IBr2+, what you see here is absolutely the correct Lewis structure. If you were to give this as an answer, this absolutely is going to be marked incorrect every single time. You need to have those lone pairs on the outer atoms and the inner atoms. You need to have the lone pairs everywhere. And so those are key and those are important. And so maybe you're asking yourselves, what is the shape of these? That's the topic of our next lecture. And so some tips when you're starting to draw Lewis structures. Don't skip the steps. Don't think ahead and say to yourself, well, I know this is what's going to happen, so I'm just going to draw this in. As you get better and better and do more of these, okay, you might be able to do that. But as you're first starting these, go very stepwise. Do not skip steps when you're writing these structures. If you don't skip the steps, you're going to come up with the right structures. As you get better and better at drawing these, you're going to just remember the rules and be able to do them. And like anything with experience and doing more, you're going to get better. And you might be able to start skipping some things a little bit because you're going to see where things are going. But as you're first learning these, just do not skip steps. Stay very stepwise and very systematic in your process. Try some of these and look at maybe some multiple, in all of these, we're going to have some multiple bonds that form. And so another thing to keep in mind as you're doing Lewis structures is that some atoms tend to form multiple bonds more often than others. And so carbon, oxygen, nitrogen, sulfur, and phosphorus might tend to form multiple bonds more often than some other atoms. And so keep that in mind. And don't worry about the models. Actually, we're not looking at that. And so a couple more things. I know this has been a long lecture, but a couple more things to look at. And so I mentioned that if there are more than one Lewis structure available, if there is more than one Lewis structure available, we analyze what we call formal charges to predict which is the most stable and which one would be most likely to exist. To calculate a formal charge, we first draw the Lewis structure, and then for each atom in the Lewis structure, we want to calculate the formal charge. We take the number of valence electrons, we subtract how many lone pairs there are around that atom, and then half of the bonding pairs. And sorry, I should redo this equation. I don't really like the way it's got the parentheses on there. But ultimately, we take our valence electrons, and then we subtract all of the electrons around it. But when we're subtracting all those electrons around it, we're subtracting only half of the actual bonding electrons. And so actually, this is good timing. We have a world-renowned expert on formal charges who would like to join us. This is Rangeley, sporting it's hunting season orange collar or orange ribbon. And so Rangeley, what would you like to say about formal charges? Is there anything you want to talk about? And he's pretty shy today. This is our Rangeley kitty. Say hi, Rangeley. Say hi to all your fans. Okay. Believe it or not, I probably got this covered. I don't need your help. Thank you, though. All right, so let's look at using some formal charges. Let's start first at calculating the formal charges here in methane. So we're going to calculate the formal charges for each atom here. So to calculate our formal charges in carbon, remember we're going to calculate it this way. He likes to help. Go on. We're going to calculate our formal charges in carbon by taking our valence electrons. We're going to then subtract any lone pairs. There aren't any lone pairs around carbon. But we do have 8 bonding electrons around carbon. We're going to take half of that for 4. So there's a formal charge of 0 around carbon. We do the same thing for hydrogens. For all of our hydrogens, hydrogen has 1 valence electron. There are no lone pairs around any of the hydrogens. And around each one, there are 2 bonding pairs. Cut that in half. That's 1, 1 minus 1, formal charge of 0 around all of the hydrogens. Here we have carbon monoxide. I'd recommend actually pausing the video and drawing the Lewis structure yourself. Make sure you can come up with the same structure for carbon monoxide, CO. But now we look at our formal charges and we see that carbon, again, comes with 4 valence electrons. We subtract the 2 lone pair. It has 6 bonding pairs around it. Half of that is 3. 4 minus 3 gives a formal charge of -1 on carbon. We do that same analysis. Valence electrons minus the lone pairs, minus half of the bonding pairs for oxygen, and we come up with a formal charge of +1. And so when you're looking at formal charges, the sum of formal charges in a neutral molecule must equal 0. If you're working with an ion, something like carbonate, CO3 2-, then the sum of the formal charges must be equal to the charge on that ion. So it would be 2- in the case of carbonate. And so that's another way to make sure that you've got your formal charges correct. They should add up to 0 in a neutral molecule and to the charge of the ion in a polyatomic. And so when we're looking at Lewis structures, if we're looking at more than one possible Lewis structure, the one that's more likely to exist will be the one that has no formal charges, a formal charge of 0 on all of the atoms. If that's not possible, then the formal charges should be as small as possible. So come up with an arrangement that has these formal charges with the least magnitude as you can. And negative formal charges should appear on more electronegative atoms. That's another key. If you end up with some sort of structure that has a positive charge on carbon, a positive formal charge on carbon, and a negative formal charge on oxygen, then that's awesome. You've got your negative formal charge on the more electronegative atom. If it's the opposite, if you have a structure that has a positive formal charge on oxygen and a negative formal charge on carbon, look at your structure and see if there's another way to arrange it so you can flip that. And adjacent atoms should not carry formal charges of the same sign. In other words, if you have a structure that has 2 carbon atoms in a row, one of them has a positive formal charge and the other has a positive formal charge, that's definitely not a good situation either. So again, look for ways to rearrange things. We talked about the charges. So go ahead and try these. So this is hydrocyanic acid, HCN. I want you to draw the Lewis structures for these and then determine the formal charges of each of the atoms in the Lewis structure, because this will tell us the best way to represent, or the best Lewis structure for this compound. So I know we talked about our rules that for the least electronegative goes in the center, but ignore that rule for just a second and draw out these 2 structures, one with carbon in the center and one with nitrogen in the center. Do a formal charge analysis, and then figure out which one is probably the best and most likely to exist. So pause the video now and give that a whirl. And so hopefully as you did this, you came up with these Lewis structures here. Let's now do our formal charge analysis on each one. Hydrogen, 1 valence electron. In each case here, hydrogen has 2 bonding electrons around it. Cut 2 in half, we get 1. So we get formal charges of 0 on hydrogen. If you ever come up with something that's not a 0 formal charge on hydrogen, you have done something wrong. So keep that in mind as well. So now our top structure, carbon has 4 valence electrons. Carbon has 8 bonding pair around it. 8 divided by 2 is 0, no lone pairs. So carbon's going to have formal charge of 0 here. Nitrogen comes with 5 valence electrons. And now nitrogen has 2 lone pair, and it has 6 bonding pair. 6 divided by 2 is 3. 2 minus 3, 5 valence electrons minus 2 minus 3. And so we have a formal charge of 0 on our nitrogen here. In our bottom structure, again, 5 valence electrons around nitrogen. We have 8 bonding electrons, divided by 2 is 4. 5 minus 4, we now have a formal charge of +1 on this nitrogen. Carbon, 4 valence electrons. Carbon has 2 lone pair minus 1, 2, 3 for half of these 6. So 4 minus 2 minus 3. We have a formal charge of -1 on this carbon. Check to see that our formal charges are accurate. 0 plus 0 plus 0 is 0. 0 plus -1 plus +1 is 0. That works out because HCN is a neutral compound. And so we can see that our top structure is the one that gives us 0 formal charges. And so that tells us that officially that would be the correct structure to draw for hydrocyanic acid. And so we'll apply this analysis anytime there's more than one possible Lewis structure. So go back to those formaldehyde examples and those different examples that we looked at with formaldehyde and apply the same sort of analysis. And so that was way back. Let's see, I'll bring it up so you can pause the video on this. There was that one. Nope, I think it was way back, wasn't it? Sorry, I should be a little more organized than this maybe. All right, I'm actually going to pause the video so I don't take up your busy time by searching. There it is. So remember we looked at this earlier where this is our correct Lewis structure for CH₂O. We looked at these other 2 possible examples. So do the same thing. Go ahead and apply a formal charge analysis to each of these 3 structures, and you'll see why this is our preferred. Sorry, I don't like this slide because this is not our correct structure. Remember, there's our correct structure. I'm not sure, I'll have to go back and fix those. So here's our correct structure. And so apply the formal charge analysis to these and see why this is our preferred structure for formaldehyde. And so that's formal charge analysis. The very last thing to look at today is what we call resonance structures. So in a resonance structure, what we'll find, actually, let's just look at an example. This is the easiest way to look at resonance structures. We're going to do our electron configuration for our carbonate ion, CO3 2-, or our Lewis dot structure. So we count up our valence electrons, 4 from carbon, oxygen, 3 times 6 is 18. Remember, we have to account for our 2-, so we're going to add another 2 electrons here. So we have 24 electrons to worry about with carbonate. We're going to put our carbon in the middle. We're going to then put our oxygens around the outside, connect them with single bonds, and then add electrons to our outer atoms. So now we've used up all 24 electrons, but we can see that carbon does not have an octet. And so we're going to go ahead and steal from one of, let's just go ahead and steal from this one. We're going to steal our electrons from oxygen there, from that lone pair, and put them into a double bond here. And there we go. There's a Lewis structure for carbonate. Now, as we look at these, or as you've done some of these, maybe you've asked yourself, well, is there a reason why I had to steal from this one? Could I have stolen from this one? Could I have stolen from this one? And the answer is absolutely. We could have stolen from any one of those. And so that means, and you can probably, hopefully reason this out and see where this is going. The one that I just drew, I had my double bond here on the bottom, and my single bonds up top. There's absolutely no reason why I couldn't have stolen from this oxygen instead. Or possibly from this oxygen. And so these 3 are what we call resonance structures of the carbonate ion. Data tells us that the reality of what exists, what actually exists for carbonate, is that the double bond is kind of spread out through all three of those. And so we sometimes draw what we call a resonance hybrid instead, where instead of drawing the double bond localized between any two, we sort of draw it like this, showing that there's in fact a double bond that exists sort of between all three of them. And so you would do the same thing with, let's say you have resonance structures that where you're moving around some multiple bonds. Actually, a great example, and we're going to leave it here for today. But if we do our structure of CO2, so we can come up with 3 different resonance structures for this. So here's one possibility. Another possibility is this. And finally, a third possibility is just with our triple bond on the other oxygen instead. Sorry, I have no idea why I just drew nitrogen. So 3 possible resonance structures for CO2. I'm just going to make that go away. There we go. And so we want to analyze which one is most likely to exist. I mean, really, the 2 on the ends with the triple bonds, those are the same. We just have a triple bond on different oxygens. And so I'm just going to pay attention to 2 of these. So if we do a formal charge analysis, so we have 2 resonance structures, could be both completely valid, both satisfy our rules for Lewis structures. But let's analyze our formal charges. So go ahead and do that. Go ahead and pause the video now and do a formal charge analysis on these 2 compounds here. Again, you could do the other one too if you want to just prove it to yourself, but it'll be the same thing, just oxygens reversed. So go ahead and pause the video and do a formal charge analysis on these, and then restart the video, and hopefully we come up with the same answers. Hopefully you came up with this here. And so we can see that, yes, where these are 2 valid structures, they're definitely 2 valid Lewis structures for carbon dioxide. The one with 2 double bonds is the structure that is more likely to exist. And so that is the one that we would say is the, quote, correct Lewis structure, because our formal charge analysis tells us so. Big sigh. A lot of information. And I know I'm saying that at the end of pretty much every lecture now. But there's a lot here. Digest it. Go back and do what you have to do. Rewatch things. Go back and look at the text to try to get it all to sink in. In our next lecture, where we're going to take this from here, is we're going to see how we can use the Lewis structures to now help us determine what the actual 3-dimensional shape of a compound is going to be. And that's going to be some big stuff too. And so that's it for today. Hope everybody has a great day, and I need to go wash my hair now. Have a great day, everybody. Happy chemistry.